Differential equations. We've done a little bit of this earlier on. This is a differential equation. We did a little bit of this earlier on. So if I say dy dx is equal to 2x, basically it's giving you the derivative. It wants the original back, right? So what do you do here to solve it? So yes, you'd multiply up the dx. Then you would do the antiderivative. The antiderivative of dy is just y, right? What's the antiderivative of 2x? Plus c, right? Yes. Okay. That's a differential equation. All right? Well, because I'm trying to get what y is. I'm working backwards, essentially. Okay? It's just when you have the derivative or the change, the rate of change, that's called a differential equation. Okay? Now, we can make them more complex. We can say dy dx is equal to xy. And then find y if it passes through the point 0 and 1/2. So if I give you an initial condition like this, then you can actually calculate c. All right, so what do I want to do here to solve this differential equation? Get all your y's on one side, your x's on the other. Okay, so if I divide off the y and multiply up the dx, I'm going to get dy over y is equal to x dx. So what operation am I going to do now? Integration. Right, because I'm trying to get rid of the dy's and the dx's. So if I integrate dy over y, what is that? The way it's written is essentially y primed over y. What's the antiderivative of that? So it's the natural log of y. Right? The derivative of natural log is y primed over y, or 1 over y. Right? What's the antiderivative of x? X squared over 2 plus c. There we go. Okay. I want to solve for y. This is the natural log of y. What is the base of the natural log? So essentially, I'm just going to write it out. Not that you have to do this every time. But it's essentially this. How do I get y by itself, if we remember grade 12 logs? Yeah. You change to exponential form. So do you remember changing to exponential form? The base moves over here, and this all kicks up to an exponent. So you end up with y is equal to x squared over 2 plus c. Grade 12 logs. But you never took grade 12. Yeah. Well, we have a week to study. Okay. So you get y is equal to e to the x squared plus c. We can clean this up even more. If you're adding exponents, what are you doing with the bases? You're multiplying them. So I'm going to rewrite this as e to the x squared over 2 times e to the c. Does everybody agree that is the same thing? It is though, right? I'm doing this. If I gave you x to the a plus b, is that the same as x to the a times x to the b?
Yeah.
That's what I'm doing. It's just I'm doing it with base e. Okay? All right. What's e to the power of c? Who said? Somebody said it. It's just c. It's a constant, right? Because e is a number, 2.718 blah. C is some constant. So anything to the power of a constant is a constant. So I'm going to rewrite it as c e to the x squared over 2. Okay? This is called the general solution. Why is this the general solution? Well, I'll show you when it'll look like this. It's because we don't know what c is. Okay? So when you don't know c, it's called the general solution. Can I figure out c? How? Yes, we're going to use our x and y values, 0 and 1/2. So 1/2 is equal to c e to the 0 squared over 2. What's 0 squared divided by 2? Okay, so then I get 1/2 c e to the 0. What's e to the 0? So what's c? So the equation is y is equal to 1/2 e to the x squared over 2. That is called the particular solution. Is that okay? Yes. Because it's a constant to a constant, which is just a constant, right? Yeah, but we don't care. It's just we just know it's a constant. The only way you can solve for c is if I give you a piece of information, another piece of information, so a point that it goes through. Okay. So instead of writing e to c, you could do it that way, but it's easier just to say it's some constant and then plug it in. Okay. Sorry.
How do we drag it down? Oh, because it's
We're good.
What if you try another point?
If I give you a different point as the initial condition, you'll get a different c value. Right? Well, I'm going to give you questions out of the book. You can do it. But we care about that. This is for the initial condition I give you. All right. You're going to see we're going to apply these to word problems. So there's initial conditions that allow you to solve for the constants, and then you can use them to solve equations later on. Okay. All right.
we didn't use any like when it was e to the c.
Yeah.
We didn't use any logarithms. We just said
no. We just said it's a constant.
So we're gonna multiply by constant.
Yeah. E to the c. Yeah. Okay. All right. Before I move on, I want you to do questions 1, 5, and 7. Yeah. 1, 5, and 7 on page 412, please. And then we're going to move on to the fun stuff. Okay. Exponential growth and decay. So if you are given an equation or a statement that says the rate of change is y prime. Yes?
Yes.
It's the same as dy dt. Because it's rate, it would be dy dt. Is in math means equals. Proportional to. Proportional means it's proportional. I don't know how to say that.
What does that mean?
But it means that there's a constant being multiplied by the other variable. It's proportional to y. So it's k times y. Okay?
And
K is a constant. You could put c, but we want to differentiate it from when we integrate it. Because when we integrate it, you're going to see the c pops up. So we want to differentiate it. Or differentiate. I shouldn't say differentiate. We want to distinguish it from the other constant. How's that? Okay? Now, if you get a statement like this, and I'm going to show you a couple of examples where this is applicable, you always get the same answer. Or the same equation, the same general equation. All right? So we're going to solve this. So we rewrite y prime is dy dt ky. You want to get all your y's on one side, all your t's on the other side. Why am I using t? Because it's rate. Yes, it's a rate of change. So, so if I move the y over and I move the dt up, I get this. All right, what do I do now? Integrate. What's the integral of dy over y? What's the integral of k dt? What? K is a constant. What's the variable?
T.
The variable's t, so what's the integral of k? Kt plus c. It's time. Right? Rate of change? Yeah. Okay. So hang on. Whoa. So we want to solve for y. How do we solve for y? We did it in a previous example. You're going to change everything to exponential form. So you get y is equal to e to the kt plus c. Yeah, so then we just did this. So it becomes e to the kt times e to the c. What's e to the c? That is the formula. Whenever you see those words, rate of change is proportional to y, or is proportional to itself, essentially, right? It is always going to be the equation y, the general equation, y is equal to c e to the kt. Okay? We'll do one example of this. All right. So let's do radioactive decay. So this is like do you remember the stuff in grade 12 logs? When we did radioactive decay and we used this formula? Remember this? Remember this? This form, and we would change the base. If it was radioactive, we'd use base 1/2. You can do everything in base E. And we like base E because in calculus, the derivative of e to the u is e to the u times du. And the integral of e to the u is e to the u plus c, right? Natural logs make things easier, especially in calculus. That's why we like base E. Before we knew them, or before we did calculus, we would always change the base, make it 1/2, or if it was doubling, it would be 2, etc. But in calculus, we want to write everything as base E. So we'll do a radioactive decay, because if you look at a radioactive decay curve, they look like this, right? This is time, and this is, I'll just say this is y, just for lack of a better term. The rate of change, the rate of change is the slope, right? Yeah? And the slope is going to be proportional to how much you have left. Okay, so it meets the demands for, or meets the criteria for this statement. The rate of change is proportional to itself. Okay, that's why it's a curve, it's not linear. So we can say, all right, well, let's just write out the question first. Breakdown. Like, do you know what half-life is? Half-life?
This is not physics.
It's like when radioactive elements decay. Yeah, okay. All right. How long for 10 grams of plutonium-239? 2 decay to 1 gram. And the half-life of plutonium-239 is 24,360 years. What?
The years that are
Oh yeah, I can see that. So Yeeb, 10 Yeeb. It's 24,360 Yeebs.
Yeah, I'm just lost. So
Okay, we'll just say slow down.
Wait, is this gonna be on the test?
Yes.
How many years?
That's probably not even that.
24,360 Pu,
Okay.
plutonium. Okay, are we ready? In radioactive decay, y primed is equal to ky. Okay? It's proportional to how much you have left. Okay? If you look at the graph of a radioactive decay curve, the slope at this point is steeper, i.e. it's decaying faster than the slope at this point. Right? So the more plutonium in this case that you have, the faster it decays. And then it starts to level out. Okay? It decays at a slower rate. So that meets this criterion. The rate of change is proportional to how much is left. We know that if you have this criteria, that you can, instead of going through all this stuff up here, you can just go, okay, well, y is going to equal ce to the kt. That's a given. You don't have to show that. Okay? We have to figure out c and k. Okay. So now let's find c. Well, I did, and then. All right. So we got to find c first. We're going to find c first. Okay? What is c? If you think about back to math 12. And this. Yes, it is. Yes. In this for it. A naught is c, essentially. It's the initial amount. Because at time t0, right? How much do we have? Y is equal to 10 grams. That's correct. So if you put it in there, just to show you, you're going to get 10 is equal to ce to the k times 0, which is 0, and then e to the 0 is 1, so you get c is equal to 10. So now we have this formula. Okay. Now this formula tells us what the initial amount is, but it doesn't tell us the decay rate. Yes. Yeah, because you start with 10, that's times 0, right? So if I put 0 into here, that becomes 0. It's e to the 0, which is 1. So y is equal to c. All right. So we have this formula. Now we got to find k. That's the decay rate. What do we know? The half-life. All right. All right. So we know the half-life. That half-life equals 24,360. Okay. How much did we start with? So what's half of how after 24,360 years, how much do we have left? 5, right? Y is equal to 5 when t is equal to 24,360 years. Does that make sense?
Yeah.
Okay, so plug those into the formula. Y is 5, 10 e to the k, and our time is 24360. Okay. How do you solve this? Well, do something first. Divide by 10. If you divide off the 10, you get 1/2 is equal to e to the k times 24360. Now what? What log? ln. You natural log both sides. If you natural log e, you just get the exponent, right? Why do we, I'm sorry? We want a natural log because our unknown is up in the exponent. So we want to get rid of the base, essentially, bring it down. Is equal to 24360 times k. And you just divide natural log of 1/2 by 24,360. And you're all going to tell me the answer. It's going to be a really small number. That's what you should get. Negative 2.84 times 10 to the minus 5. Is that right? Okay. And if you want the units, it's actually years to the minus 1 or per year, or whatever you want to do it. Okay. But I'm not worried about years. I'm not worried about the units, okay? All right. But if it was. So now our formula is y is equal to 10 e to the negative 2.84 times 10 to the minus 5 t. I don't know. Is it? I don't care anymore. 2.85, I guess. Whatever. All right. What was the original question? Because this is 24,000 in years, and we divided it, so it's in the denominator. And that makes sense because when you in this formula, time is years. So this would have years in the denominator because when you multiply them, you want the years to cancel. Look, I'm not worried about the units. Okay, they will work out. You just have to have them in the same units, but you're not going to see one where it's not. Okay, so the original question was how long until 1 gram? What? No, 1 gram is how much we have left, right? That's the rate. When it says proportional to, it's the constant that you're multiplying, how fast things are changing. Okay.
The long 1/2, we just divide it off.
Sorry?
But that long 1/2, we just divide it off to the side.
No, I went. I did that. All right. Okay, so how long to 1 gram? So it's 1.0 is equal to 10 e to the negative 2.84 times 10 to the minus 5 time. Okay, people, wow me with your mathematical skills and tell me the answer. I got 80, but it depends on where you round, so it's fine as long as you're close, right? Because we're talking like the difference between 79,000 years and 80,000 years is irrelevant, basically. I think it's 5. Yeah, I got 80, 80-ish, 80-ish thousand years, 81,000 years, whatever. When you're talking about this amount of time, it's not that big of a deal.
I put 8079.
That's perfect. Okay, so moral of the story is when it says, where does it say? The rate of change is proportional to y. In other words, how fast it's changing is proportional to how much there is, i.e. in a radioactive decay. The general formula will always be C e to the kt. You just have to find C, which is the initial amount, and then K, which is how fast things are changing, and then you can solve whatever question you need to solve. Okay? 21, 23, 29, and 37 on page 4112, please. We have one more thing. We'll do that tomorrow. Test on Monday.